Before we start with the first argument, please keep in mind that when we talk about load shedding, we should always be aware that the complete breakdown of an industrial plant due to a blackout usually costs much more than the acquisition of any load shedding system. Furthermore, it should be observed that due to the phase out of fossil energy, our grids are coming close to their limits. Here as well, load shedding offers functional advantages. So let's start with reason number one. It's a typical well-known use case. Imagine that this is your industrial power grid. If a power source like the infeeder from the public grid trips and there are no compensation measures, then the frequency will begin to decline. Depending on the characteristics of the industrial grid, this drop of the frequency will reach within short time the trigger point of all generator protection devices. This means a complete blackout for the entire production site. By using a fast power-based load shedding system, the loss of a power source is compensated within a few milliseconds by switching off low priority consumers. This prevents a blackout and keeps the impact on production as low as possible. Reason number two, also this is a typical use case. In many industrial applications, the different processes normally do not run simultaneously. For this reason, the power generators are not designed to cover the maximum possible power consumption. However, if the power restrictions are not observed and too many consumers are switched on, then there is no longer balance between available and consumed active power. In this case, again, a frequency drop will occur. As mentioned in the previous slide, an uncompensated frequency drop will lead to a blackout with a complete loss of production. This scenario can be effectively avoided by the installation of a load shedding system. Reason number three is a more sophisticated use case. Usually, the energy consumption of an industrial plant from the public grid is limited by contracts. It is a common practice to monitor the consumption in time periods of 15, 30, or 60 minutes. If a plant exceeds the contractual limit, high penalties may be accrued. A load shedding system can also monitor such contractual limits. In the shown example, the start of the energy monitoring was selected for minute 7. The load shedding system automatically extrapolates the energy consumption of 1 minute. If a violation of the contract is predicted, the load shedding system sheds the necessary number of low priority consumers. This procedure will be repeated until the end of the monitoring period. This function makes it easy to prevent possible effects of the contractual violations. Other algorithms for predicting energy exceedance are also possible. Reason number 4. Also, this is a more advanced use case. Usually, the technical limits of transformers and infeeders are only monitored by protection relays. If the transformers or tie lines are overloaded, then they will be completely tripped by these relays. Load shedding installations can offer a much smarter approach. Just before a protection device switches off an entire transformer or a feeder, the load shedding system can shed the required number of connected low priority loads. This significantly reduce the negative impact on the plant's production. Now we come to the last and maybe most up-to-date reason. Driven by the climate crisis and increased energy costs, many utility grid operators try to shift from classic electrical energy sources to renewable energy, such as wind or photovoltaic plants. But this also means that power reserves in the power grid will become much smaller. This fact may force operators of public grid to motivate industrial customers to help in stabilizing the grid frequency. Such a motivation can be achieved by offering lower tariff models. The installation of a load shedding system in the industrial plant enables compliance with such possible tariff models.